Have you ever wondered what your muscle actually looks like? What your bicep would look like if you were to go underneath the skin and into the muscle? Well, if that's a question you've had, then you're in luck, because today's episode is all about Year 12 ATAR Studies Unit 3 Functional Anatomy. Let's do syllabus point number 1. The structure of skeletal muscles. The first part of the skeletal muscle is the muscle belly, which is formed from bundles of long muscle fibers. Then we have the epimysium, which surrounds the muscle belly, holding all the fibers together. Then we have the endomysium, which is the connective tissue which is around the muscle cells. And then the perimysium, which surround the muscle fibers. And muscle fibers are groups of myofibrils. And there are two types of myofibrils, and they are a combination of the smallest units of muscle, actin and myosin. Actin is the thin filament and myosin is the thick filament, and both are different types of proteins. And together they make up sarcomeres. Now we are moving on to the sliding filament theory. Now, going through the image, we have myosin, which is the thick cross bridges, and they run parallel to actin between each filament and in the middle of the sarcomere. Then we have actin, which is the thin filament and is attached to the Z lines. A sarcomere is the contractile unit of a muscle and is made up of overlapping myosin and actin protein. The H zone only has myosin and is in the center of the A band, and the I band only has actin. The A band is where the actin and myosin overlap, like so. So this is the sliding filament theory. It looks like this. When a muscle contracts, it becomes shorter, and when it extends, it becomes longer. So concentric and eccentric contract. The Z lines form the boundary of the sarcomere. Now we are moving on to muscle contractions and the relationship between velocity of a muscle contraction and the amount of force exerted by that muscle contraction. It takes time for sarcomeres to contract. Rapid movements do not allow complete contractions of the sarcomere. So, for example, if you wanted to quickly kick a soccer ball, you're not going to be able to kick it as far as if you were to take your time and sequentially kick that soccer ball with more force. For more force, more time is required. And the lighter the object, the greater the velocity that can be produced. Maximum force is generated from isometric contractions. So for example, in a rugby scrum and a plank, that is the maximum contraction the body can create compared to a leg extension or running. Power is the combination of strength and speed. So in long jump, in powerlifting, you need both to be successful. Now we are moving on to the relationship between the length of a muscle and the potential force it can exert. Force length is talking about the length of a muscle and the joint at which the angle is, and the impact that both of those variables will have on the force produced. There are 3 parts of force length. You have shortened, mid-length, and lengthened. The optimal position of force generation in terms of length of a muscle. So this would be lengthened of the bicep, this would be mid-length of the bicep, and this would be shortened length of the bicep. The optimal force generated out of these 3 positions is the mid-length, near the middle of the joint range of motion. This position allows maximum attachment of the myosin bridges with the actin. So when you're doing a bicep curl, you'll get the most force generated around this movement here, which is why we do half reps or third reps. So you can just go up here or down here. Now we are moving on to the CNS, PNS, and motor neurons. So CNS and PNS stands for the central nervous system and the peripheral nervous system. Both of these nervous systems allow for our brain to connect to our muscles and our body to allow for movement to occur or to create movement. The CNS includes the brain and the spinal cord, and the PNS includes all our other limbs of the body. Within the PNS, we have something called motor neurons and sensory neurons. Motor neurons transmit neuro messages to the muscles from the CNS, so from the central nervous system to your muscles, and sensory neurons transmit messages from your muscles to your brain, so they are opposite. A motor neuron is made up of 3 parts. You have dendrites, which act like TV antennas and receive information from the CNS to the body. The dendrites, and then you have the axon, which is where the message transmits along, And then you have the cell body, or the nucleus, which controls the activities of the neuron. So when it receives the signal, it can transmit it along the length of the axon. And then a bunch of motor neurons together is what makes up a motor unit, and the muscle fibers that it innervates. So you have a neuron and the dendrites, and then it connects to muscle fibers. Those two parts are what we call a motor unit. Now we are moving on to the all or nothing principle, which falls underneath the relationship between muscles and nerve functioning. The all or nothing principle states that if an electrical stimulus reaches a certain threshold, then all of the muscle fibers associated with that unit will contract to their maximum level, and all at the same time. It's like turning a light on. If you flick the switch, the light will go on. Not part of the light, all of the light. So when you flick the switch to your muscles, that whole muscle will contract. You can't do a movement half-heartedly. Even though you might not do it at a certain percentage, all the motor units that are contracted will all contract at 100%. When we're talking about doing something at 50% or 70% or 100%, like kicking a ball, so it's not to do with if the muscle fiber is 100% or not. They are always 100% if they're used. It's determined by how many are used at 100%. So for example, in large muscles like your quadricep, you might have hundreds and thousands of muscle fibers in there that get recruited, compared to your eye muscles, which might only have a few. Then we have neuromuscular responses to strength training. Often when you first start going to the gym, you won't see visual adaptations or changes straight away. It usually takes a few weeks. This is because to see the change in the bulk of the muscle, there are a few things that need to happen first. The first one is improved technique to allow more muscles to actually be recruited, so mind-muscle connection. Sometimes I see people doing bicep curls and they're using their whole body. You're not going to build your bicep if you're actually relying on the other muscles around it. Often I tell my clients or myself when I'm doing a bicep curl to stand up against a wall that keeps your elbow fixed and only requires you to use your bicep curl. So you can do the preacher bicep curls too. That's where you'll gain the most improvement. Increased firing rate of the motor unit. More motor units need to be recruited. So that's when we talk about mind and muscle connection and recruiting more units of muscle fibers. And finally, the firing pattern needs to be improved. And finally, we have muscle fiber types. Have you ever been asked what muscle fiber type you are? Or have you ever heard someone say, Usain Bolt is so fast because he has type 2B muscle fibers? And you're thinking, what the heck is type 2B muscle fibers? Everyone is born with a different type of muscle fiber, just like you're born with a different type of blood type. There are 3 different types of muscle fiber. They have a big impact on the relationship of what activity you'll succeed the best in. So, to start with, we have type 1 muscle fiber. Characteristics of this muscle fiber is they're slow twitched. So often they have a slower muscle fiber contraction, meaning they're better at aerobic type activities. So long distance runners, long distance swimmers, they are often smaller in size, the actual motor unit, and they are red in color because they carry oxygen. A great example of someone that has type 1 fiber characteristics is Ned Brockman. He is a great example as he is able to run for long periods of time and continue through the hardship that he might come across. Now, this is not to say that he wouldn't succeed in a long jump or sprinting or powerlifting competition. However, it is important to note that when you're born with a certain muscle fiber type, you are at a competitive advantage. So someone like Ned Brockman could train to be a 100-meter sprinter, but he probably will never get as close to Usain Bolt because Usain Bolt already has that advantage in his muscle fiber type. So moving on from type 1, we have type 2A. Now type 2A is a nice mix between type 1 and type 2B. It is a fast intermediate contraction of the muscle fibers. It is low endurance and it uses the anaerobic energy system. They are large in muscle size and they appear white as they don't contain oxygen. Now a good example would be 400-meter runners and 4-kilometer runners. Finally, type 2B muscle fiber types are fast, explosive muscle fiber types. They contract fast and explosively. They are very low in endurance. They use the anaerobic energy system. They are massive. They are large in size, so big contractile motor units, and they appear white as well. A great example is Usain Bolt.